So the transistors, you probably approached them through these equations in previous classes. There we go. And there's three equations. There's cutoff, which I have as approximately 0. It's actually not 0. There's actually a current equation for transistors in cutoff, and it's exponential. It's very small current. It's a very small current. It may be nanoamps, but it still is not 0. And then there's linear, and there's active, which you may know as saturation or pinch off. If you use a different textbook, you use different names. I'm using cutoff, linear, and active, just because whatever I say about MOSFETs is probably true about BJTs, and whatever I say about BJTs is probably true about MOSFETs. And so we might as well talk about them at the same time. But the word saturation means two different things for MOSFETs and BJTs. So I've picked these three as how I'm describing the regions of operation. You want to know these other names in case you get an interview or either explain what region of operation you're talking about. If you just say active here, linear and cutoff make sense to everybody, but calling this active doesn't make sense to everybody. Okay. In this class, we're actually we're hoping we're not in cutoff or linear. We're hoping we're in the active region. And the reason we like to be in the active region is because that's where you get the most current and the most current change. When you have an amplifier, the output of a transistor is actually current. It's not voltage. And the way you get a voltage is you take the current that comes out of the transistor and throw it across a resistor. A resistor is the simplest current to voltage converter there is. So it's not the transistor that creates the voltage, it's the current out of the transistor being thrown across a resistive component that gives you a voltage. Okay. So what you want from your transistor is you actually want the region of operation that changes the current the most. If you change the current more, that means the voltage changes more and you get a bigger gain. And since we're in this class, we're going to be trying to build an operational amplifier. And operational amplifiers, like a large gain, we're always going to want to be in this region. And for almost everything we build, really everything we build in this class, we want to be in the active region. And in lab, if you have trouble with the circuit, first thing you probably want to check is check VGS, check VDS, find your VT, see if you're in the linear region, and that might be, that is very often one of the reasons why you're not getting what you should in lab, just your transistors in the wrong region of operation. So again, we're really not interested in these two regions of operation. We want to use this, we want to be in this region of operation so as to get the maximum current change. And excuse the dog in the background grunting. And for PMOS, these are the exact same equations. The only difference is that everything, all the voltages and currents are negative. Actually, the way I have this written, it will be positive, but yeah, so exact same equations, but things that are required. Notice over here, IDS is positive, VGS is positive, VT is positive, VDS is positive, K prime is positive. When you go to K prime is negative. I'm going to check that. But for PMOS, you can use the exact same equations, but you just have to go back afterwards and make sure that your VGS and VDS are negative. So you can use the exact same equations, but then you just have to go back and do a second check and see if VGS and VDS are negative. Okay. the VT, you may have been treating it as a constant voltage up to this point, but it actually isn't. When the source voltage is different than the substrate voltage, if there's a VSB, source to bulk voltage, then your threshold voltage is actually not the VT in your model file or data sheet. Okay. This is one of the graphs that I hope you're familiar with and comfortable with. It has VDS or VCE on the x-axis, and then IC or IDS on the y-axis. Okay. And for each one of these lines, they're a constant VBE, or some textbooks have constant IC, but we're going to be assuming a constant VBE if we're talking about BJTs. And then between each of these lines, I'm increasing VBE by the same amount. But notice that for this change in VBE between these two lines, there's not much change in the current. But between these two lines, there's more. Between these two lines, it's more. And between these two lines, it's more. So for the same change in VBE, you get a big jump in current. And that is, remember, when you have a transistor, its output is current, and you throw that current across a resistor, a big change in current means a big change in voltage. And a big change in voltage means you made V out move a lot, which means it had a lot of gain. And a lot of people look at this graph and look at this point and say, oh, that's steepest, that's where you get your big gain. But what's important is, again, transistor's current output, and that current output is getting thrown across a resistive component. If you look at this, between in the active region here, or saturation region, or forward active region, you get this much change in current when you go from this VBE to this VBE. But over here, you only get this much change in current. So you're actually not getting a big change in current when you're over here. This is the linear region, and you don't get all that big a gain. The last graph that's important, I'm not going to go over because hopefully you've seen it in 307 and 306. But this is the second graph that is important. And on the x-axis, it's either VBE or VGS. And on the y-axis, it's IC or IDS.